Welcome back, Math 1910, Calc 1. We're in Chapter 4, Section 6. We're going to go through numerical integration, basically covering the trapezoid rule and Simpsons rule to approximate areas under the curve. So kind of the last method for being able to solve the area problem. And then come up with, approximation and errors because, with the trapezoid rule, it's kind of like, when we did the rectangle rule and we're doing trapezoids instead of rectangles, so there's going to be a slight amount of error. It's not going to be the exact value of the area under the curve. So let's take a look at the trapezoid rule. So very similar to when we did, rectangular rules, left hand, right hand sums and those sort of things. We're now making trapezoids, and you can see in the picture here, in the figure, where we're taking the area of each trapezoid. So notice that some of the trapezoids are above the curve, some are below the curve. So we're going to get as close as we can to the curve. All right, and just like we did with Riemann sums and things like that, based on the number of intervals or the number of trapezoids we take, okay, the more trapezoids that we do, the more accurate our value will be versus the less number of trapezoids that we do under the curve, the less accurate we will be. But they're both approximation methods to find the area under a curve. Okay, so remember, it's kind of like you still need to understand the area of a trapezoid. Okay, so the trapezoid still has base 1 plus base 2 times a half times the height sort of scenario. So we have to make sure that we're still using the area of a trapezoid to follow this, and then we have to do it for ith trapezoids there's going to be a general formula for finding it for multiple trapezoids, but essentially we're drawing trapezoids under the curve. So here is Theorem 417. Okay, it's the trapezoid rule, and we're going to let the function be continuous on a closed interval from a to b. So we can use the trapezoid rule here. The integral from a to b of f of x dx is going to be approximately b minus a divided by 2n, okay, where n is the number of trapezoids that we're going to do. And we can see that it's going to be this sort of sum. And the coefficients will change. See how there's a 2? We're going to increase the coefficients, and you'll see in the example, as we do more trapezoids. So you'll kind of see how that varies out. But it must follow suit here as we substitute in. So it's going to kind of have a pyramid effect. We're going to build up to the middle piece and then go back down as we evaluate using the trapezoid rule. Okay, so we're going to do an example here. We're going to do the same example with the Simpsons rule as well, but we want to use the trapezoid rule to approximate the area under the curve from 0 to pi of sine of x. And we're going to do this, and we're going to compare the results for if we do it with 4 trapezoids versus if we do it with 8 trapezoids. So notice, it still is that pyramid effect where it's going to, be down. So we're going to have 2 bases, right? Remember, base 1 plus base 2 divided by 2 is going to be the average of the base pieces times the height that we're going to have for each trapezoid. And notice that the height is going to be the interval spacing. So between pi over 4 and pi over 2, between pi over 2, 3 pi over 4, right? That's still the spacing there with pi over 4. So the graph here shows if we used 4 trapezoids versus if we used 8 trapezoids. So notice if we used 4 trapezoids, there's a slight space there underneath the curve and the trapezoid. So when we use 4, we're going to be approximately less than the curve. Now 8, there's going to be a little bit less of a space. You can barely see it there at the top. But as we increase the number of trapezoids, the more accurate our approximation is going to be. Alright, so let's jump right in. We're going 0 to pi sine of x dx, and we're going to use the trapezoid rule to approximate the area. So when we do that, okay, all I'm doing here is we are following suit with the trapezoid rule here. So if I step back a couple slides, it's this piece. So notice b minus a divided by 2n. That's the leading piece here. That's where we're getting pi over 8. Okay? Okay, so it's b minus a divided by 2n. Alright, so b minus a in this case is going to be what? Pi minus 0 okay, divided by 2 times 4, right? Because 4 is the number that we're taking. So that's why the pi over 8 is in front, okay? Our change in x is because we're going to go pi over 4 here. So if we step back, we can find out, how to calculate what our dx is, okay? Because we want to do 4 intervals, right? So remember, we're going from 0 to pi. That's the difference in the limits, and we want to take 4, 4 trapezoids. So pi minus 0 over 4. So that's where our delta x is going to be pi over 4. Okay, so now we substitute in each pi over 4. Okay, and we're substituting in here. So we have f of x0 plus 2 times f of x1 plus 2 times f of x2. Alright, that's these pieces. And then we're going to go back down the other way. 2 times sine of, I'm going to step back here, of f of x to the n minus 1. Remember, n is 4, so that's why it's going to be x to the third. Alright, and then f of x again at the end point. Okay, so we're going to start at 0, and then the next value is going to be pi over 4, because our delta x is pi over 4, right? So 0 to pi over 4 is our first increment there, so that's why we're going to have sine of 0, because sine is the function, right? Pi over 4, that's the first step. And then we're going to go pi over 4 again, right? Between pi over 4 to pi over 2 is a distance of pi over 4. That's still our delta x. Okay, and then we're going to have to go between pi over 2 and 3 pi over 4. That's another pi over 4. And then we're going to do another one. So from 3 pi over 4 to pi, that's our last pi over 4 increment. So we have, 4 different delta x's, but we have to apply it to the trapezoid rule so that we actually have to run through the function, right, 5 times, if that makes sense. So that's really what we're doing, substituting into the trapezoid rule. So now we just have to apply this. Okay, so it's going to be pi over 8 times sine of 0 plus 2 sine of pi over 4 plus 2 sine of pi over 2 plus 2 sine of 3 pi over 4 plus sine of pi over 2. So notice on this, the outside two terms, the sine of 0 and the sine of pi, don't have any coefficients in front, and notice that all the middle terms are going to have a coefficient of 2. And then we just need to, go back to our trig and evaluate each one. So it's going to be pi over 8. We know that sine of 0 is 0. We know that 2 times sine of pi over 4, right, is going to be square root of 2. It's really like, square root of 2 over 1, but same concept there. Or square root of 2 over 2, and the 2's cancel, so that's where we get the square root of 2. And then we know that sine of pi over 2 is 1, so 2 times 1 is 2. And then we have sine of 3 pi over 4. Remember that that's square root of 2 over 2, and then the 2's cancel, so we're just left with square root of 2. And we know that sine of pi is 0. Alright, so we're able to simplify all this down. And when we do that, and we get a decimal answer, we get that it's approximately 1.896. So we just apply the trapezoid rule. It's really just, substituting in our values, finding our delta x, alright, based on our number of trapezoids that we're going to do, and then we just evaluate using the trapezoid rule. So let's do it when n is 8, okay? So remember, it's going to be b minus a all over 2n, so that's where it's going to be pi minus 0 divided by 2 times 8, because now n is 8, so that's why we have pi over 16 in front, okay? And then our delta x is going to be pi over 8 now, right? Because it's pi minus 0 divided by n is 8. So we're going to do this in increments of pi over 8. So this should be relatively easy for you, right? We're going to start at 0, and then 0 plus pi over 8, so we go to pi over 8. And then between pi over 8 and pi over 4 is another pi over 8. Between pi over 4 and 3 pi over 8, that's another pi over 8. So you can see that each increment between each one of these two sine functions is going to be pi over 8. So if you count, right, since n is 8, we're going to have 9 different terms that we got to evaluate. Just like the previous part of the example, when n was 4, we had 5 different terms that we had to evaluate. So you always evaluate terms, one more term than what your n is. So once again, the first and last term, the sine of 0, sine of pi, those don't have coefficients, and all the coefficients in between are 2. So this one's relatively, easy. I'm not going to walk you through the trig of evaluating all these like I did the first part, but it's really basic in how we set this up. All right, so remember the delta x is going to be pi minus 0 over n. N is 8, so that's why it's pi over 8 for the delta x. Okay, so that's why we're stepping through all of that. Then you're going to evaluate the function at each one of those increments. All right, and then you're going to simplify down. So we can see, all right, in this scenario, we get 1.974. So when n is 8, and we do this with 8 trapezoids, we get 1.974. And then I'm going to step back a slide, right? When we did it with 4 trapezoids, we got 1.896. So we can see just the difference alone in the two approximations. As we increase the number of trapezoids, the more precise we get. All right, so we can also do another method. We could do Simpsons rule. Okay, it's a way to view the trapezoid approximation of a definite integral. If we have like a first degree polynomial or something like that, or a second degree polynomial, or those sort of things, we can use Simpsons rule. Okay, so Simpsons rule is as such. Notice, slightly different pieces here. We're going to do b minus a divided by 6. That will always hold true. So instead of using n now, we're going to do it there. So this is theorem 4.18. If we have a polynomial in the form of ax squared plus bx plus c, okay, we are going to integrate it as such. So notice the first term is p evaluated a, last term is p evaluated at b, and notice each increment in between is going to be a plus b divided by 2. And that's where we're going to evaluate the function. Okay, so write down Simpsons rule, and then we're going to apply it. Notice the function in between is going to be 4p. All right, if we want to do it for, a greater one, okay, we're going to use Theorem 4.19. What I'm talking about, if we have, more, we're going to do, an even integer and things like that. Okay, so we're going to take the integral from a to b of f of x dx, and it's going to be multiplied by b minus a over 3n. Okay, so n is however many that we want to use, trapezoids, or how many intervals actually we just kind of want to take with the function. Okay, so it's very important that you understand how we build this up and take the approach. So that's why we're going to do the same exact integral using Simpsons rule instead of using the trapezoid rule on this. So write down Simpsons rule, and then we'll kind of see how to approach it. Okay, so we're going to use the same example we just did, 0 to pi of sine of x dx, same integral. We're going to do it for n equals 4 and n equals 8 for our approximations. So literally we are just going to substitute everything in. So now notice that it's what? It's pi over 12 in front, because if we step back and look at this, it's b minus a. Okay, so that's going to be pi minus 0 divided by 3 times 4, which is 12. So that's where our pi over 12 in front comes from. Okay, and then, all right, we want to do our x1, x2, x3, x4. That's still the same piece that we're evaluating. So that's still going to be pi minus 0 divided by n, which is 4 in this case. So we're evaluating sine at all the same pieces. Now, what's different, okay, what's different with Simpsons rule is look at the coefficients. Where the trapezoid rule, all the leading coefficients were 2. With Simpsons rule, the 2 is not until the middle term. Okay, so all the terms between, so the left term and the right term, sine of 0, sine of pi, have no coefficients. That's the same. The middle coefficient is 2. That's the same. And then the 2 in between coefficients are 4. So notice that that's the difference in Simpsons rule. And if we step back and look at it this way, this is how it's going to build up. And you'll see the difference between if we do 4 versus 8 when we do this. All right, but now, guys, the rest of the part's similar. It's just being able to set up and apply Simpsons rule or set up and apply the trapezoid rule. Now it's just literally evaluating each one of those pieces, multiplying by pi over 12 at the end. And so with Simpsons rule, and we evaluate with 4 intervals, we get 2.005. Whereas the trapezoid rule, right, I think we had 1.86 when we did our approximation. So Simpsons rule is slightly a little bit more exact when we do this. All right, now let's do Simpsons rule with 8. All right, now, I'm not going to go through all the work. You're able to substitute in all the values and do that sort of thing. When you do Simpsons rule with 8, it ends up getting you 2.003. So more accurate. All right, and we're getting in closer and closer. We know if we plug that into our calculator and we integrate from 0 to pi over 12, or 0 to pi of sine of x, we get 2 if you do that, okay? So we just know that, Simpsons, we're going to be a little bit above. Trapezoid rule, we might be a little bit below. And how do we know? We can do some error analysis, okay? So we can do some error approximations, all right? We want to find the error, okay? It's the difference between the integral and the approximation. Because notice, the trapezoid rule and Simpsons rule, those are just approximations. The integral is the actual function itself. So here's how you set up those errors, or to calculate the error, not setting up for error, but how we calculate an error. So if we want to find the error for a trapezoid rule, okay, it's going to be b minus a quantity cubed divided by 12n squared. Remember, n is still the number of intervals we're taking. So with the trapezoid, when we did the 4 or when we did the 8, okay, or okay, and with the Simpsons rule, it's b minus a to the 5th divided by 180 n to the 4th. Now, what you have to pay attention to is the derivatives here. For the trapezoid rule, we're going to use f double prime of x. For Simpsons rule, see how there's an f to the, in parentheses, 4? We have to take the 4th derivative of the function to use Simpsons rule. And remember, this is strictly to find the error. So very important that we understand what we're using and how we do that here. All right, so we want to determine a value of n such that the trapezoid rule, all right, will approximate within an error that is 0.01. And we're going to do that to this integral here from 0 to 1 of the square root of 1 plus x squared dx. So we want to be within an error of 0.01. All right, so what we're going to do, we're going to find the second derivative because we're using the trapezoid rule here. All right, so it's important we have to find the second derivative. Why? Because that's part of the rule right here. See where it says max absolute value f double prime of x. So we're going to apply and find the second derivative. I'm not going to walk through all the steps. You should know how to do that. So we find the second derivative of the function. So we have to find the maximum value on that interval from 0 to 1. All right, remember the max occurs or the min occurs, right? We're looking for extreme of when the second derivative is 0. So we can say, we can set f double prime of 0, so 1 plus x squared to the minus 3 halves. If we set that equal to 0 and solve, all right, it happens at 1. Okay, so using the theorem now, we have the other piece. We have to do b minus a quantity cubed divided by 12n squared. We're going to times it by f double prime of 0, which we already know is 1, all right? And we know b minus a, so that's 1 minus 0, so we get 1 on top, all right? So in general, our solution is going to be 1 over 12n squared, okay? When we do that, now n is, we have to choose, the correct n so that we want to be within that specific error. So if we want our error to be less than 0.01, you have to choose n such that 1 over 12n squared is less than or equal to 1/100th. Okay, so when we substitute those in, right, 1/100th, that's our 0.01. So to do the error piece here, we literally just solve that, right? We set it equal to 1/100th and then solve for n squared. So we take 1 divided by 12n squared, okay? Because that's all the calculation we did for the error. We're going to set it equal to 1 over 100 because that's what 0.01 is. It's a hundredth, okay? And then when we set those equal to each other, we end up saying, all right, 100 is less than or equal to 12n. Divide both sides by 12, square root. We only want the positive answer. So as long as n is greater than or equal to 2.89, we will have an error that is less than 0.01. All right, so that means we need to choose n at least, probably at least 3 intervals so that we have a more accurate value instead of, something that's way off when we do our calculation. Okay, so let's do this. If we take a look here and we do our calculation, all right, using our value of n equals 3 to the trapezoid rule, and we apply the trapezoid rule. This is what we just learned in the first part of the lecture, so nothing real new here. And you substitute everything in, we get 1.154 using the trapezoid rule. Now, down below, if we integrate, okay, we know that we have to be between 1.14 and 1.164 because that puts us within 0.01. All right, so if you take 1 plus or 1.154 plus 0.01 and 1.154 minus, all right, 0.01, that's where we're getting our values of 1.144 and 1.164. So we know that the integral has to lie somewhere between 1.144 and 1.164 when we do the calculations. Okay, so that's very, very important. So that's how we calculate our error estimate using the trapezoid method. So that's the end of this lecture. You would do the same kind of concept if we did a Simpsons rule, just a little bit more involved with Simpson error because you got to take the fourth derivative. I won't make you do too many of those calculations just because they're kind of mundane and you could do them over and over and over, and you got to take a lot of derivatives. But you guys get the idea, understand how to approximate the error, so that you can say, all right, the integral lies within, these two answers, and we are within 1/100th of where we need to be. So that's the end of this lecture, guys. As usual, email me if you have any questions. Let me know if you need to team meet, Zoom meet, or anything else like that. Else, guys, have a great day. I'll see you in class. We'll be doing more examples in class. All right, have a good day.